Hello and welcome to today's lecture on interfacing to the media. We have discussed various techniques such as encoding, modulation and multiplexing, with the help of which you can transmit signal over medium, over any transmission medium. Now, question arises, how do you interface your equipment to the transmission media? It can be twisted pair, coaxial cable or optical fiber or wireless medium. Whatever it may be, you have to interface your equipment somehow to the transmission media. That is the topic of discussion of today's lecture. Here is the outline of the lecture. First, we shall discuss the basic concept of interface, where it is required. Then we shall discuss the various modes of communication between the interface and the user equipment, maybe the computer. The various modes or transmission techniques are parallel and serial, or it can be simplex, full duplex and half duplex, or there are two types, asynchronous and synchronous transmission. And then we shall discuss about the interface between two equipments like DTE, data terminal equipment, and data circuit communicating equipment. So, these two interface between these two have some standards. One of them is EIA, Electronic Industries Association, developed this standard EIA 232. We shall discuss about it in details. Then we shall discuss the concept of null modem which is related to this, and another interface, although which is not that popular, is X.21. Then we shall discuss about the modems which are actually connected to the medium. And on completion of this lecture, the students will be able to explain various modes of communication, distinguish between half duplex and full duplex communication. They will be able to distinguish between asynchronous and synchronous modes of communication, and they will be able to specify the RS-232C or EIA 232 standard used for DT-DC interface. They will be able to explain the function of a null modem, and finally, they will be able to explain the functionality and standards used for modems. Let us see what do we really mean by the interface. We have seen, to send data to the transmission media, we have to do the encoding, various encoding techniques we have discussed in detail. Now, that encoded data has to be transmitted, and for that purpose it is necessary to interface data terminal equipment. By data terminal equipment we mean the computers and various other equipments. It can be computer, it can be printer, plotter, it can be any other equipment which can transmit, receive data. And the link between, and then another equipment will be required, that is known as DCE, data circuit terminating equipment. That data circuit terminating equipment will actually interface to the medium. As you can see here, data circuit terminating equipment is now sending the or launching the signal on the medium. And obviously, we have to develop interface between this data terminal equipment referred to as DTE and data circuit terminating equipment DC. This interface is an electrical circuit, and how we can send digital signal over this, all these are to be discussed, and some standard has to be used for this purpose. So, we shall discuss about this interface in detail. Before that, let us discuss about the various modes of transmission, or rather possible modes of communication. Data can be transmitted in parallel or in serial. Again, parallel has two different types, synchronous and asynchronous, and serial also has two different variations, synchronous and asynchronous. First, let us consider the parallel transmission technique. In parallel transmission technique, as you can see, a number of bits, usually a byte or a word, it can be either a byte, that is 8 bit, or it can be word can be 8 bit, 16 bit, 32 bit, or 64 bit, depending on the size of the processor. It can be byte or word, that is sent in parallel. As you can see, all the bits are transmitted parallel between the sender and receiver. Obviously, whenever you transmit data in this manner, it is very fast, because all the bits are going simultaneously. However, this is possible only over a short distance, and this parallel transmission is commonly used for transmission of data between the CPU and memory, or between the CPU and other peripherals which are very close to the CPU. That means, when two equipment are located very close, that means within few feet or meters, then this parallel mode of communication is possible. So, usually parallel mode of communication is not popular in the data transmission techniques that we are discussing in detail, and in that respect normally serial transmission is used. What do we really mean by serial transmission? As you can see, in serial transmission, a pair of wire is used for communication of data in bit serial form. You are, instead of sending in parallel, you are sending bit by bit. As you can see here, you are sending first 1, then 0, then 1, then 0, then 1, then 1, and 0 and 1. So, in bit serial fashion, and of course, this will require parallel to serial conversion at the send by the sender, and also it will require serial to parallel conversion at the receiving end. However, it has many advantages for and that is particularly it is very suitable for long distance communication. That means, the serial mode of communication is possible over long distances. So, here the various reasons for using serial transmission is given, and in this lecture we shall mainly focus on serial transmission, and let us see what are the various techniques or why serial transmission is required. First of all, it allows you reduced cost of cabling. As you have seen, we are using lesser number of bits at a time, only we are sending one bit at a time. So, you require one pair of wire, you do not require a bunch of wires. So, it requires lesser number of wires compared to parallel connection. In parallel communication, you require a bunch of wires to be connected between the DT and DC, which is not required here. Then it leads to reduced crosstalk. Because of lesser number of wires, it results in reduced crosstalk. We have discussed about this crosstalk in details, and we have seen whenever a number of wires are bunched together, it leads to crosstalk. And here in the serial mode of communication, crosstalk is reduced significantly. And third important factor is availability of suitable communication media. We are familiar with telephone system, microwave system, and satellite network. In all these cases, data transmission takes place in serial form. That means, if you have to use the popular transmission media like telephone network, satellite network, or microwave network, we have to use serial mode of transmission. Fourth point is there are many devices which have which are inherently serial in nature, and in such cases it is natural to use serial mode of communication. For example, whenever we read data from some devices like tape recorder, tape, discs, floppies, hard disk, there it is always serial in nature. Another important factor which is becoming important in the present day context is the availability of portable devices like PDAs, cell phones, and in such cases we have seen the PDAs, cell phones, these are very small in size, and if we use a parallel connector having large number of pins, it is very difficult to fit in a PDA or a cell phone. However, if we use serial mode of communication, the number of pins required is small, so the connector size is also small. So, only small connector size can be used in for portable devices, and that is why serial mode of communication is can be used in such cases. However, as we shall see, the serial mode of communication is slower than parallel mode of communication. It is much slower compared to the parallel mode of communication that is possible when we are sending data in parallel form. For example, when we are sending data between computer and main memory, their data transfer rate is very high. We cannot transfer data at that rate, however, that may not be required in most of the applications. Let us see the various modes. First one is simplex mode. Here, as you can see, data is unidirectional. Here data is going from sender to the receiver. There is no data going from the receiver to the sender. It is flowing from only in one direction. For example, this can be a computer and this can be a printer. So, in such cases we can use simplex mode of communication. However, simplex mode cannot be always used. As you can see, in some situation it has to be in both directions. So, here it is bidirectional. For example, here you have got one computer and here you have got another computer. So, when two computers are communicating with each other, it is quite natural the data transfer will be in both directions. This is known as full duplex. On the other hand, the previous one, when it is unidirectional, it is known as simplex. So, for full duplex communication, as you can see, we require two wires, two pairs of wires for communication of data simultaneously, because here it allows simultaneous communication in both directions. That is why it is called full duplex. However, there are situations in which it is not possible to have two separate transmission links or channels. So, in such cases we have to use what is known as half duplex communication. In half duplex communication, as you can see, you have got only one channel, but communication is taking place in both directions. Obviously, the communication cannot take place in both directions simultaneously. In such case, we have to use some protocol. For example, when a policeman is talking to his headquarter, you will find that he is talking, then he is telling over, then again listening for some time, then he again starts talking. So, they have a single communication channel through which the headquarter is communicating with that policeman. So, in such a case, the technique is known as half duplex. That means a single communication channel is being used for communication in both directions, but in one direction at a time. This is known as half duplex communication. Then comes the other two techniques, that is asynchronous and synchronous. Let us see what do we mean by asynchronous serial transmission. In asynchronous serial transmission, what is being done, instead of sending long sequences of bits at a time, bits are grouped either in bytes or words, and then each such character can be a byte or a character, that is 7-bit ASCII code. So, these are one is sent at a time, and it is sent in the form of a frame. As you can see here, there is a frame for sending one such character, and each character is framed with the help of a start bit in the beginning and one stop bit, 1 to 2 stop bits at the end. That means, each character has a start bit and 1, 1.5 or 2 bits of stop bits, and there is an optional parity bit, and the character size can be 5 to 8 data bits. So, you see we are not sending more than 8 data bits at a time, and that 5 to 8 data bits is being framed with the help of a start bit, stop bits, and if necessary parity bit for error detection. Now, whenever a sender is not sending data, the line can remain idle, or that is that is you are sending essentially 1, idle state of line is 1, and whenever data transmission is start, the line is made 0, signifying that a word is being transmitted, and the data transmission ends with the help of stop bits. So, after immediately sending the stop bit, one can send another word. In such case, next start bit will start, or it may remain idle like this. And in this case, the receiver has the opportunity to resynchronize at the beginning of each new character. So, here you can see, before a particular character is received, the receiving end can synchronize with the help of this start bit, and this has many advantages, as we shall see. So, here it is shown how several characters have been sent from the sender to the receiver. Here you can see one character has been sent, then there is a gap, and that gap can be indefinite. There is no, I mean, it can be of any duration. Then another character is sent, then there is a gap, and then another character is sent, then there is a gap, and so on. And it has been found that this technique is very simple to implement. That is why it is very widely used. This is quite widely used, and one important characteristic is it is self synchronizing. So, we have seen that whenever data is sent by the sender, at the receiving end it has to be received and in a synchronized manner, so that a 1 is received as 1, a 0 is received at 0 at proper bit position. If it is not received in that manner, then it will be incorrect. Here what is being done, as you have seen, it is synchronized with the help of the start bit at the middle of this start bit, then it is sampled at the middle of each of these bits. So, as a result, it gets synchronized with this particular edge, rising edge, and then at the middle of each bit it is the data is sampled, and to find out whether it is 0 or 1. And as a consequence, the timing requirement is modest. Even if the receiver clock is 5% slower or faster, signal can be received correctly, because the synchronization is done for each character separately at the beginning of each word. But it has some limitation. The limitation is arising because of additional bits like start bit, stop bits, which is increasing the overhead. For example, you are sending 8 bit. To send 8 bit, you may require 1 stop bit plus 8 data bits plus maybe 1 parity bit plus 1 stop bit, 1 stop bit. So, 1 start bit, 1 these are the data bits, this is parity bit, and this is start bit. So, stop bit. So, you require altogether 11 bits to send 8 data bits. So, you see there is the that means 3 by 8, that is roughly about say 30 by 300 by 8, that is roughly about 4%, about 40%. So, 40% overhead is here. That means, to send 8 bits of data, 3 additional bits are required. So, about 40% overhead is there, and also you can think it in another way. Here you are sending 11 signal elements to send 8 bit data. That means baud rate is 11. You can say if you send 8 bits per second, then you are sending essentially 11 bits per second signal. That means 8 bit data and 11 bit signals per second. That means the baud rate is 11, bit rate is or data rate is 8. So, baud rate is higher than the data rate. You can think in this manner. So, this high overhead cannot be tolerated in many situations. In such a situation, we have to go for another alternative, that is your synchronous mode of communication. So, in synchronous mode, what is normally done? Initially, 1 or 2 synchronization characters are sent instead of start bit and stop bit for each character. Data characters are then continuously sent without any extra bits. So, you are not sending start bit and stop bits for each character, and at the end some error detection data may be sent if necessary. The advantage is here the overhead is much less, less than 1%, maybe 0.01%. So, this kind of overhead is present in synchronous mode, and as you can see, there is no overhead except for the synchronization characters. Synchronization characters are however necessary to identify the beginning of a block of data. However, the main disadvantage here is there is no tolerance in clock frequency. You cannot accept any tolerance, because you are sending a large number of characters. If there is mismatch in frequency, after few bits the receiving end will receive incorrect data. That is why here it is necessary to transmit in fully synchronous manner. And here is the synchronous serial transmission, how it is being done. A block of bits is transmitted in a steady stream. Here is the data field. It can be very large, it can be say few kilobits, and this is there is a preamble, 8 bit flag and some control bits, and there is a postamble control fields, can be error codes, error correcting codes and error detection codes, and 8 bit flag which is postamble. So, preamble, postamble is provided along with the data, but the percentage of overhead is very small. So, here the synchronization is done at higher level using preamble and postamble bit patterns, as I have mentioned. So, special character is sent in the beginning at the end to mark the beginning and end of a stream of data, and this is the synchronous frame format. Now, here one question arises. We have told that the clocks of the two ends must be fully synchronized. How it can be done? One alternative is to send separate line for, a separate line can be used for sending clock. Then at the receiving end, that clock will be used for receiving data, but that is not practically feasible unless two systems are located very closely. So, in such a case, the normal practice is to recover data, recover clock from the received data with the help of some suitable hardware known as phase lock loop. But that phase lock loop will require some transitions, and we have seen different encoding techniques we have discussed in detail, which are used so that synchronization is possible, and clock is recovered with the help of phase lock loop at the receiving end. So, the synchronous serial transmission will require complex clock recovery circuit so that synchronization is possible. Now, coming to the question of interfacing, we have seen that we have data terminal equipment. It can be computer or any other equipment which can send data or receive data, and we require a DCE, data circuit terminating equipment. This data circuit terminating equipment will launch the signal in this communication system, and at the other end another DCE will receive that signal, and it will then send the signal to the DTE at the receiving end. and in between you will require interface at both ends between the DT and DC. So, to DC is usually the modems, as we shall see, and DT are computers and various other equipment that we use for sending data. Now, the interface has to be universally accepted, so that the two equipments, one DC and DT, manufactured by two different companies, can be interfaced. For that purpose, some standards are to be used, and standards have been developed by two organizations, the EIA, Electronic Industries Association, and ITU-T for the DT-DC interface. And as you can see here, the standards developed by EIA is known as EIA 232, EIA 442, and so on. And similarly, the ITU-T standards are known as V series or X series standards. Here we shall primarily discuss the EIA standards, because these are very popular. And as we shall see, this interface will require three different components: mechanical, electrical, functional, and procedural. And let us see what are the different components do. So, here the EIA 232 standard, which has got different versions A, B, C, and D, presently D. The mechanical specification specifies the connector type. You will require a connector and a cable to connect to equipment. So, the mechanical standard specifies that, and in the main standard a 25 pin male and female connector have been suggested, and these connectors are used for linking a DC with a DT. However, all the 25 pins are not used, 9 of them are commonly used, as it is shown in this particular diagram. So, subsequently a DB9 9-pin connector have been developed, which is commonly used. This is smaller in size, and the various signals that is present on these pins are also shown here. Then the electrical specification gives you the logic levels, the maximum cable length, and the maximum data rate, baud rate, which can be used for communication between DT and DC. As you can see in EIA 232C, the electrical signal levels are not TTL compatible, that it is not 0 volt for 0 and plus 5 volt for 1. So, it is not true. So, as you can see here, for logic 0 the range is plus 3 to plus 25, usually plus 12 volt is used. On the other hand, for logic 1, minus 3 to minus 25 volt is used. In practice, minus 12 volt is commonly used for this purpose. So, we see the electrical specification specifies the electrical voltage levels, the maximum cable length, and the maximum baud rate. So, these are the three parameters specified by electrical specification. Then comes the functional specification. It specifies what are the different signals that you require, signal lines that you require, and they can be broadly divided into 4 types: data lines, control lines, timing lines, and ground lines. And for EIA 232C, basically 9 lines are used, as I have shown here. For example, this is a ground signal, then this transmit data and receive data, transmit data and receive data. These are the data lines. Then your carrier detect, DC ready, cleared to send, ring indicator. These are the signaling signals, those timing signals, and some of them are control signals. I shall explain the function in the next specification, that is the procedural specification. This procedural specification specifies the sequence of events that will take place for transferring data. So, to send data you have to use a sequence so that the transmitter and receiver can communicate with each other. it is some kind of protocol, the agreed upon protocol that is being used for the communication between the two systems. For example, DSR, data set ready, and data terminal ready are used to check whether both devices are ready for communication. That means, these two, DSR and DTR, will be used for establishing the fact that both are ready for communication, both have been turned on. On the other hand, the request to send and clear to send, these are the handshaking signals for transferring before transmission of data can be started, and the transmit and receive, these two are used for transmitting data between DC and DT. Let us see how it is exactly being done. So, here we see a DT on one side, DT on the other side. This is a DC, modem A, modem B, and connected through a transmission media. So, first the DT sends the DT ready signal to the modem. In response to that, and also it sends the that telephone number, that it is connected through the telephone system. So, telephone number is sent through the data lines. So, in receiving that, the modem sends the ringing signals that goes to the other end, and whenever the modem receives it, a ring indicator signal go to the other end DTE. In response to that, the DTE sends, DTB at the other end sends that DT ready signal, which informs the modem that DT is ready for receiving data, and in response to that, a carrier signal is sent by this modem B to the modem A, and after receiving that carrier signal, modem A sends a DC ready signal informing that this DC or modem is ready for transmission, and in response to, and also it sends a carrier signal to the other end, and after receiving that, modem sends a signal detector to the DTB, and now the system is ready for communication. A link or channel has been established. Now, the both DTs are ready for communication. How it is done? Let us see. So, here as you can see, before transmission of data, the DTA sends a request to send, informing the modem that asking the modem whether it can send data or not. In response to that, modem responds giving a signal, handshaking signal known as clear to send, and after receiving that, the DTA will send the data, transmitted data, and which will go to the other end, and as it goes to the other end, as you can see, the DTB will receive the data. After receiving the data, the communication is complete. This is how at the beginning of each communication, for sending each character of data, request to send, then clear to send, and this is followed by transmission of data to the other end. So, this is how character by character is sent one after the other between two DTs. So, apart from RS-232C, RS-232 the standard, some other standards have been developed by Electronic Industries Association. I am briefly comparing the RS-232C with two other standards, RS-423 and RS-422. The reason for that is that RS-232 was developed long back when the data rate requirement was much smaller. As we have seen, only 20 K bits per second can be sent, which is very low in today's standard. So, to improve the performance, this RS-423 and RS-422 were introduced. As you can see, the baud rate here is more, 300 K for RS-423 and 10 megabits per second for RS-422. And then the cable length is also increased. Instead of 50 feet for RS-423, it is 4000 feet, and also for RS-422, it is 4000 feet. And these are the output voltage levels, +5, plus 25 to I have already explained, plus 5 to plus 25 for 0 and minus 5 to minus 25 for 1. On the other hand, for RS 4 to 3 is plus 3.6 to plus 6 for 0 and plus 3.6 minus 3.6 to minus 6 for 1, but here it is 2 to 6 volt between outputs. Here it is balanced. Balanced means differential, as you can see. Differential means the data is sent between two wires. When it is unbalanced, you are sending data through one wire and there is a common ground line. On the other hand, here there is a common ground line, but the data is sent between these two wires. That is why it is called balanced. This helps to reduce the noise, because all the noise passes through the signal. As a result, whenever you use unbalanced or single ended communication, there is noise immunity is much less compared to the balanced mode of communication. Here, because of higher data rate and longer distance, this balanced mode of communication is necessary. So, input threshold is in this case minus 3 to plus 3 for RS232C, and here the threshold is much less, minus 0.2 to plus 0.2, and same is true for RS422. So, these are the input resistances. Here high input impedance 4K, more than 4K, here it is 3K to 7 kilo ohm. So, in brief, this is the comparison of the other standards, and here is a important concept known as null modem in the context of this DT-DT interface. We have seen that whenever the data transmission has to take place over long distance, the two DTs will require two DCs, and then through telephone network communication can be done. However, when two DTs are in the same room, the same interface may be used, but there is no need of any DC. In such a case, the concept of null modem is used. That means, whenever the communication is over a very short distance, there is no need for any DC. However, we can make use of the good old RS232 or EIA232. How it can be done is explained here. So, instead of this DC telephone network and DC at the other end, this is being replaced by a cable. So, null modem is nothing but a cable, as you can see. However, the wires are swapped. It is because it is transmit line. So, transmit signal has to go to the receive line, and this transmit signal has to go to the receive line. So, a null modem is nothing but a cable with two female connectors at both ends. In the previous case, here we use female connector, here we use a male connector. Similarly, here is a female connector, here is a male connector. But in this particular case, we have to use female connectors at both ends, because both ends are DTs and wires are swapped as necessary for communication between two DTs. But the important point is DT is fooled here. DT has the illusion that it is connected to a modem, but in practice it is not. It is connected to a cable, and that cable is connecting to the other DT. So, this is the null modem concept. Whenever we have to use that 25 pin connector, some of the wires have to be looped back and some of the wires has to be cross connected, and various cross connections and loop back lines are shown in this null modem when 25 pin connectors are used, that is used in the standard RS232. Another standard which have been proposed by ITU-T to overcome the limitations of EIA232 is the X.21. So, this X.21 was designed by the ITU-T to overcome the limitations of EIA232 and pave the way of all digital transmission. That RS232 was developed in the era of analog transmission or analog communication. On the other hand, that X.21 was developed to facilitate digital transmission. What has been done here? Most of the control circuits are eliminated by data traffic, so that the number of pins required is small, and it is replaced by data traffic, that means with lesser pins, but data lines are used for sending the control signals, and it works in balanced circuits as I have already explained, and data rate is 64 kilobits per second. So, it is relatively high compared to 20 kilobits per second, and it uses a 15 pin connector which is known as DB15 connector, and there are various timing signals used for byte control. Here it uses timing lines for byte control, and pin 3 and pin 5 which are control and indication are used for handshaking, as we have seen that request to send, clear to send are used in case of RS-232. Here that control and indication lines are used for that purpose. So, in brief, this gives the overview of X.21. Now, we shall require another important component for interfacing DT to the communication media. We have seen that interface, now the modem is required, and we have already discussed modem in details. As you know, a modem stands for modulator plus demodulator. So, it performing two functions, modulation and demodulation, and a modulator, as you know, converts digital signal into an analog signal using ASK, FSK, PSK or QAM modulation techniques, which we have discussed in details earlier. And the demodulator converts an analog signal back into digital signal. Here there are two important parameters, as you know, the transmission rate and the baud rate. Here are the various baud rate and data rate explained based on different modulation techniques. As you have seen, the using smaller baud rate we can achieve higher bit rate or data rate. It can be, if we use 256 QAM, it can be 8 times. For example, if we are using the typical telephone line having the bandwidth of 2400, that is the baud rate, and so we can multiply it by 8 if we use 256 QAM, that will be the data rate. So, 8 into 2400, that can be the data rate in this particular 256 QAM. And some modems have been developed by ITUT and Bell Laboratories. Bell Laboratories are known as, the modems developed by Bell Laboratories are known as Bell modems, and ITUT developed modems are known as V series modems. So, some of the standard modems are shown here, and they are, some of them are equivalent, as you can see. V.21 is equivalent to Bell 103 Bell modem having baud rate of 300, bit rate of 300, and modulation used is FSK, and V.22 is the ITUT standard, and Bell modem standard is 212 having baud rate of 600, bit rate of 1200, it uses 4 PSK phase shift keying, and V.23 which is equivalent to Bell modems 202 uses baud rate of 1200, bit rate of 1200, uses FSK phase shift keying, frequency shift keying. V.26 Bell modem equivalent is 201, uses baud rate of 1200, bit rate 2400, using 4 PSK phase shift keying, and V.27 uses it is equivalent to Bell modem 208, baud rate of 1600, and bit rate is 4800 using 8 PSK, and V.29 which is equivalent to Bell modem 209 provides baud rate of 2400 with bit rate of 9600, that uses 16 QAM. And there are other standards and providing at most 33.6 kilobits per second of data transfer using modems. That is the maximum possible data transfer rate possible in using modems. Now, here is the standard modem operation explained, how it is connected to the telephone network and how it works. As you can see, this is the DT or the computer, and here are the modems, and this is the interface. It can be RS-232C, RS-232 or EIA232, whatever you call it, and these are the two modems at both ends, and these modems are connected by local loop to the switching exchange, and in the switching exchange it is converted into digital form by using PCM, and so that digital data goes through the digital telephone network and to the telephone network, and at the other end it is again converted by inverse PCM, and that goes to the other side of the modem, and again that interface is there which is connected to DTE. That is how the communication take place, and because of the quantization possible, quantization is done in PCM, we have to, it is the data transmission is restricted by Nyquist rate, which we have already discussed in detail, and based on that maximum data rate possible is 33.6 kilobits per second. So, data transmission rate is not really very high, you cannot go beyond this when you have got this system. However, nowadays another types of modems which are becoming popular, which are known as 56K modems. You may be asking how it is possible to transmit at such high rate of 56 kilobits. Does it violate Nyquist criteria? In practice it is not. Let us see how it is being done. This 56K modems can be used when the other end is not connected to the standard analog telephone system, but it is digital one, which is essentially the internet service provider. As you can see, there are two types of signals present here. One is going from this DTE through the modem to the local loop using the PCM, and it goes to the internet service provider. So, in this uploading direction, data transfer rate is still 33.6 kilobits per second because of the presence of PCM here in this particular direction. However, when the data is being sent by the internet service provider through the digital telephone network, then there is no PCM involved here. The data is going through the inverse PCM, and it is going through the local loop to the modem. In such case, the data transmission rate possible is 56 kilobits per second. So, in the downloading direction or downlink direction, as you can see, high the data transfer rate is possible in the reverse direction. So, the reason for that is, in this case that PCM is not present. So, that Nyquist, no question of quantization error and no question of violation of the Nyquist rate. So, we find that the 56K modems allows you data transmission at higher rate from the internet to the user, and which in particularly in that direction we require higher data rate. Usually we are downloading more data from the internet, then we are sending towards the internet. So, here is the 56K modems. So, in summary, in this lecture, to summarize, in this lecture we have discussed about the interface between the data terminating equipment, that is your computer and other peripherals, and the data circuit terminating equipment or DC, which is commonly a modem, and the standard interface, that is EIA232, has been discussed in detail. Other standards also we have discussed briefly, like X.21 and some other standards proposed by EIA, like EIA422 and EIA423, and we have discussed the operation of modem, how modem communicates through the telephone network between two DTs, and also we have discussed the function of the 56K modem in detail, how it provides you higher data rate. Now, it is time to give you review questions on this lecture. Here the first question is, distinguish between half duplex and half duplex and full duplex transmission. It will be full. distinguish between half duplex and full duplex transmission. Second question is why serial transmission is commonly used in data communication instead of parallel transmission. Third question is distinguish between asynchronous and synchronous serial modes of data communication. Fourth question is what is null modem and when can it be used. Fifth question is in what way standard modems differ from 56K modems. These questions will be answered in the next lecture. Coming to the answers to the questions of lecture number 13, first question was distinguish between the services provided by cable TV and HFC networks. Answer is the standard cable TV service allows distribution of broadband TV signals to a large number of people. Here data transmission is only in one direction. On the other hand, in HFC, that hybrid fiber coaxial network, the data transmission is in both directions. So, in addition to broadcasting TV signal in the downstream direction, it allows broadband internet service which is bidirectional through the cable network. Second question was how the upstream bandwidth is shared by a group of users for data transfer in HFC network. As we know, only 6 channels are available in the upstream direction. So, each channel is shared by a group of users in the same neighborhood. For this cable modem, the cable modem has to negotiate with the CMTS in the distribution hub. You know that CMTS is present in the distribution hub to contend for a channel. Then the CM can send data to the internet in the already allocated channel using TDMA, time division multiple access. So, this concept of multiple access will be discussed in more detail later on. Then the third question was how is an STS multiplexer different from an add drop multiplexer. Answer is an add drop multiplexer operates in the line layer of SONET and it can add signal coming from different sources into a given path or remove a desired signal from a path and redirect it without demultiplexing the entire signal. On the other hand, STS multiplexers operate in the path layer and it either multiplexes signal from multiple sources into a STS signal or demultiplex an STS signal into different destination signal. We have seen that STS multiplexer signal is responsible for converting electrical signal to optical signal and optical signal to electrical signal. Fourth question was what is the relationship between STS and STM. The standard developed by ANSI is known as Synchronous Optical Network SONET, whereas another very similar standard developed by ITUT is known as Synchronous Digital Hierarchy or SDH. Their relationship is shown in this table. As you can see, OC1 is not present in SDH has no SDH equivalent. On the other hand, OC3 is equivalent to STM1, OC12 is equivalent to STM4, OC14 is 48 is equivalent to STM16, OC192 is equivalent to STM64, OC768 is equivalent to STM256. These are some of the popular signal levels shown here, and we have already discussed in detail the line rate, payload rate and overhead rate for the different levels. The final question was how does SONET carry data from DS1 service. The answer is to make SONET backward compatible with the current DS hierarchy. The frame design of SONET includes a system of virtual tributaries in which more than one tributaries are interleaved column by column, and SONET is also provided with the mechanism to identify each VT virtual tributary and separating them without demultiplexing the stream. So, with this come to an end of today's lecture. Thank you.